All right, get ready to dive deep. Today we're tackling Einstein, but don't worry, we're leaving the equations behind. We're on a mission to uncover the philosophy behind relativity. Forget my M sign. This is about how Einstein thought.
It's true, most people know the highlights, but this is different. We're going back to 1923, a lecture Einstein gave, and it reveals how he wrestled with the very foundation of physics. Like we're getting a glimpse into his thought process.
It's like time travel for physics geeks. So where do we even start with something this big?
Well, he starts simply. What does it mean to be in motion? Can we even say something is truly still?
You'd think physics figured that out ages ago. Pretty basic, right?
You'd think. But that's Einstein for you. He saw a problem, a clash between what Newton's laws said and what we actually observe.
Hey, now I'm hooked. What was the problem exactly?
So Newton had these inertial frames, basically things either at absolute rest or moving straight and steady. Those were the gold standard for measuring motion back then.
So Newton believed in true stillness, and Einstein disagreed.
Exactly. He said that clashes with a basic fact. We only ever see relative motion. Think about it. Right now, you're still compared to your chair, but moving compared to, say, the sun.
Yeah, like on a train, you see another train, and for a second you don't know who's moving. It's just relative.
Right. Einstein said, forget stillness. Let's build on what we actually see. Relative motion.
But how do you build an entire theory of the universe on something that shifty?
That's where it gets really interesting. See, even something perfectly still, like, say, a building, it's all motion at the atomic level. He used the example of a rigid body to illustrate this.
Rigid body, like a rock, a skyscraper.
Exactly, but Einstein argued even a rock is atoms in constant motion. Like he was saying, even seemingly solid things don't give us perfect stillness.
So no fixed reference point. He really shook things up. Where do you even go from there?
He realized to move forward, he had to shift focus from absolute motion to something much deeper, the speed of light. And trust me, this is where it gets really wild. So one of the big things with special relativity is that the speed of light, in a vacuum that is, it's constant for everyone.
Wait, constant. So like if I'm running towards a beam of light, it's not coming at me faster than if I stood still.
Nope, same speed. It's weird, right? Think of a car, you drive towards it, speeds add up, bigger impact, light. Doesn't care how fast you go towards it or away, always that same speed, about 300,000 kilometers per second, every time.
That's just wild. But if light speed has a hard limit, doesn't that mess with, everything else? Speed is just distance over time, so speed's fixed, but motion's relative.
You're getting it. To make that work, Einstein had to rethink time itself.
What? You mean time like seconds, minutes? That's not constant either?
That's what he said. Time isn't absolute. It's relative to whoever's observing. It's all woven up with space, what he called space-time.
So my time is different from someone moving differently relative to me. My brain's bending a bit here.
It is mind-bending. And this space-time warping, this relative time, it's not just theory. It's been proven. GPS, the thing in your phone, it wouldn't work right without accounting for relativity, both special and general, in fact.
So Einstein's in my phone, keeping me from getting lost. Okay, I see why this was a big deal for physics. But we keep saying special relativity. Didn't he have a general one too?
He did. And that's where it gets even wilder. See, special relativity was amazing, but it mostly handled constant speeds, straight lines. Gravity, though, still needed work.
Right, because what's gravity got to do with all this space-time stuff?
Another thought experiment. Imagine you're in a box, can't see out. Suddenly you feel pulled down. Could you tell if it's Earth's gravity or maybe you're in a rocket accelerating up so it feels like gravity?
Tough one. Honestly, I don't think I could tell the difference.
Exactly, and that's the core. Gravity and acceleration, their effects, they're basically the same. Equivalence principle, he called it.
Okay, so far, I'm with you. But how's that a new understanding of gravity itself?
This led Einstein to maybe his biggest idea. Gravity isn't a force pulling from far away like Newton thought. It's all about space-time being curved.
Space-time. Curved. That's kind of out there. How does that even work?
Picture this, a bowling ball on a trampoline. What happens?
It makes a dip.
Right. Now roll a marble across. Does it go straight?
No way. It'll curve around that bowling ball, follow the dip.
Bingo! That trampoline, that's space-time. The bowling ball, that's a massive thing. Like the sun's mass warps space-time around it, a kind of gravity well.
So Earth isn't being pulled by the sun, it's just following this curve the sun makes.
That's the idea. Gravity's still real, but it's not a pull. It's the shape of space-time itself, warped by mass and energy. That's what we feel as gravity.
That is amazing. Something we experience every day, this invisible pull, and it's all about the universe's fabric being warped. Just wow.
It is remarkable. But even figuring all this out, space, time, gravity, Einstein knew there were still mysteries left.
More mysteries. After all that, what else could there be? Seriously, more mysteries. After all that, what else could have possibly stumped him?
Well, one thing that really fascinated him was this idea called Mach's principle. It basically asks, what if inertia, the thing that makes stuff resist changing its motion, what if that's actually caused by the gravity of everything in the universe all pulling on each other?
So instead of just saying an object at rest stays at rest, we're saying it's actually everything else in the universe holding it in place with gravity.
Yeah, kind of wild, right?
Yeah.
Einstein, he liked the idea, but he couldn't quite make it fit with general relativity. And even today, physicists are still debating Mach's principle, doing new research to see if it holds up.
Wow, so even our best theory of gravity might have missed something. You said there were two big questions. What was the other one that really grabbed Einstein?
This is a big one. He wanted to unify gravity with electromagnetism. So in physics, we've got these four fundamental forces, right? Gravity, electromagnetism, the strong and weak nuclear forces. They run the show.
And he was looking for a link specifically between gravity and electromagnetism.
Exactly. He spent years, especially later in his life, searching for what he called a unified field theory. He figured there had to be some elegant way to look at it, some underlying principle, where both those forces were actually just two sides of the same coin.
So, like you showed, space and time were connected. He was hunting for that same kind of connection, but for two of the most fundamental forces out there. Did he ever find it?
He didn't crack that nut, unfortunately, but by searching so hard for that unified theory, he opened up whole new avenues of physics research. Even now, people are still chasing that dream, a theory of everything, stuff like string theory, quantum gravity, all come from that impulse he had.
It's humbling, you know. This guy, he changes how we understand the universe, and even he knew he wasn't done. Shows how much is still out there to discover.
And that's the best part of science, isn't it? It's not about knowing all the answers. It's about the journey, asking the questions, pushing those boundaries. Einstein's legacy isn't just the theories, it's that curiosity, that willingness to challenge what we think we know, even the really big stuff.
It can feel intimidating, right? It's learning about someone like Einstein, and you think, what can I possibly add to that? But this whole deep dive, I think it reminds us to never lose that curiosity.
Couldn't agree more. He proved that sometimes the biggest breakthroughs come from questioning the things we take for granted. If time and space aren't what we thought they were, then what else might we have gotten wrong? What other revolutions are waiting for us?
That's a great note to end on. So there you have it. From what it means to move, to the nature of gravity, to chasing that ultimate unified theory, we got a glimpse inside the incredible mind of Albert Einstein. And hey, who knows, maybe this got your own gears turning. Maybe the next big breakthrough is already brewing in your mind.